All right, we ready for some improper integration?
Ready something like that. I hate to tell you, Julian, but world domination starts past Calc 3, not Calc 2.
Oh,
Yes.
oh.
You
Be
gotta-
patient, Julian.
Yeah.
World domination is not here yet.
They don't teach you that until much later.
Okay, so integration of improper integrals is sort of a really important topic. You're going to see it in differential equations. You're going to see it in lots of engineering courses when you do things like Laplace transforms, which you will see in multiple classes, and they have like the most unbelievable, it's just an unbelievable process that works for solving crazy equations. The basic idea of a Laplace transform, just to give you a little heads up, we know how to integrate continuous functions really easily, but there's a lot of data in the real world that's not modeled with continuous functions. Like if you think about alternating current with electricity, right? It's going one way, then it jumps, goes the other way, it goes the other way. So you have a non-differentiable function that represents that. So these pictures on the board, not only are they continuous, they're also smooth, right? They're differentiable. So Laplace transforms are pretty slick because you use an improper integral and you can take a non-differentiable function and you can move it over to the Laplace domain with an improper integral, create a continuous function, do a bunch of calculus on it, and then convert it back to what we call the time domain, and you can solve all sorts of problems that way. So Laplace transforms are going to be things that you're going to be, they'll blow your mind once you get to
Laplace,
them.
my man. He's got a demon. He's got.
All things. All things.
Can't wait.
Yeah, so you'll first see them in DiffyQ, the Laplace transform. But it's based on improper integration, and when you get into an engineering program, you'll see Laplaces in at least 3 classes, so super important to get the improper integration down, because that's how you're going to do those Laplaces. So what the heck's an improper integral? You know, we never talked about a proper integral. What's an improper integral? Going straight to the improper. So here is what an improper integral is. We have to get a little bit of terminology dialed. When we look at this curve here, a lot of times they're looking at Bell-type curves with improper integration. But the main idea is that if we look at the right tail of this curve here, it goes on forever. Right? This area goes on forever. It doesn't mean that the area is infinite, but it does mean that the area is unbounded. So we want to distinguish, when we say the area is infinite, it truly means that the area is infinite. It's like an infinite number of square inches or infinite number of square miles, infinite number of square centimeters, whatever. That's different than the region being unbounded. So unbounded means that it goes on forever, and we are going to see that the area doesn't necessarily have to be infinite even when the region is unbounded. And so then you say to yourself, well, wait, isn't area a sum of rectangles? And yeah, when you're thinking about area, you should be thinking by now, you're thinking about a bunch of these little rectangles that are added together. They each have positive area, right? So then all of a sudden it boils down to this fundamental question. Can you add an infinite collection of positive numbers together and get a finite result?
Yes.
How? Give me an example.
I don't know the answer to that. That's why I took this class.
Example?
A half plus a quarter plus an eighth plus 16th and so on.
Yeah, that's a good example. That will work. I can give you a simpler example, but that's a good example. That is true. 0.3 is a positive number. 0.03 is a positive number. 0.003 is a positive number. And if we add this infinite collection of positive numbers together, we get a third. Right? So we've just sort of short-circuited one of those things that most people find counterintuitive, that you could add an infinite collection of positive numbers and get a finite result. Like, that seems counterintuitive. But as soon as you see that example, you're like, oh yeah, of course. right? You think of all those repeating decimals, those are infinite sums. Those are adding, all these things, 0.9 plus 0.09 plus blah, 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 right? You're adding an infinite collection of positive numbers. Every single number there is positive, and you're getting a finite result. What does this add up to?
0.99.
1.
Yeah.
0.9 repeating, which is the same thing as 1. 0.9 repeating and 1 are the same number. Decimal representations of numbers are not unique. If 0.9 repeating and 1 were not the same number, there would be a distance between them. And we can prove that there is no distance between them. If you spit out a number and say, oh, the distance is 0.1 million zeros and then a 1, I can say, no, it isn't, and show you that you're right. We can go further out with the 0.9 repeating and show that if there is a distance, it's got to be less than that. And so by contradiction, we can show that there is no distance between them, which means they're the same number. Think about this. If you multiply this by 3, you get that. If you multiply that by 3, you get that. All right, so decimal representations of numbers are not unique. And you can, in fact, very easily demonstrate that you can add an infinite collection of positive values and get a finite result. Just because you add an infinite number of positive numbers doesn't mean you get an infinite result. Now, one of the classics we are going to see that is infinite is this. If we add this group of positive numbers together, this will turn into an infinite sum, like a sum that is infinite. That is not going to be finite. That one is called the harmonic series, which you will see a lot in this class and in future classes. So that's called the harmonic series, and the harmonic series, we say that this series diverges. In other words, it doesn't converge to a number. It doesn't approach a number. So one of the features for an infinite sum to be finite is if you look at each term, the terms have to be shrinking to 0, and they have to be shrinking to 0 pretty quickly. If you look at the harmonic series here, these terms are shrinking to 0, but what we will show eventually is that they are not shrinking to 0 fast enough. And so it's necessary that these terms approach 0 if you're going to get a finite answer when you add an infinite number of numbers together. In order to get a finite result, these have to be going to 0. But just because they're going to 0, that's not enough. We need to show that they're going to 0, and we need to show that they're going to 0 fast enough. Which that's what this chapter is going to be partially about, and then when we get to infinite series, that's going to be what that chapter is all about. Is figuring out, okay, they're going to 0. It's pretty easy to determine if they're going to 0, right? You can see if they're shrinking to 0. The question on whether they're going to 0 fast enough, that's the crux. That's what we have to figure out. Okay, so an improper integral, in its essence, is trying to determine if an unbounded region has finite area. That's what an improper integral is. So a definite integral, you can see the limits of integration. You can see that the region is bounded, right? You're just trying to find the area beneath the curve. That's a definite integral. Kind of a proper integral. You know the area is finite, proper. Here, you look at this area and you're like, I don't know if it's finite or if it's infinite. The area goes on forever, but that's not what we mean by infinite area. When we say infinite area, we mean that the square inches, the square centimeters are infinite. So just because the region is unbounded, you still could have a finite area. We just need to get that terminology straight, that a finite area can apply to an unbounded region. Unbounded means it goes on forever. Okay, so we have 3 types in this first slide 3 types of unbounded regions. We have one that's unbounded to the right, we have one that's unbounded to the left, and then here we have a region that's unbounded in both directions. So that's kind of our first step, is to deal with these things. And then we're going to go to functions that are unbounded vertically. So these are unbounded horizontally. The horizontal tails go on forever and ever. The horizontal tail or tails. So here's how we do it. Well, we know all about definite integrals. And so what we do is create a definite integral. So this one wants to go from a to infinity. So we're starting at a. And what we're going to do is lop off the tail. And we're going to find the area between a and b, which is a definite integral. We can find that. Right? That's just a regular definite integral. But this a is a number, right? This number right there gives us the left endpoint. B is just going to be a placeholder. So that b right there is not a number, right? We're going from a to infinity. We can't just pick 10 or 20 or 30. So what we do is literally pick b and say that b is bigger than a. We're just going to let b be a variable. And so when we evaluate this definite integral here, this will end up being a function. It'll be a function of b. Right? And we've seen that already this semester. If you find a definite integral and there's a variable in the limit of integration, you end up with a function. Right? If you have 2 numbers as your limits of integration, you end up with a constant. And we called the variable inside a dummy variable because it just disappeared once you integrated. You integrate and you get your x squared over 2, plug in your 2 limits, and you get a number. Right? So a definite integral typically gives you a number, but if you have a definite integral where there's a variable in one of the positions, one of the limits of integration, you end up with a function. And then once we get this function, then we just do our classic Calc 1 thing, and well, let's take the limit of the function. And let's see if this function is going to represent the area from A over to B. It's representing this area. So we're getting a function that represents that area. Then we just take its limit and see if that function has a finite limit. If it has a limit, that's a real number. Or is the limit infinity? So that's kind of the idea. With a tail to the left, so this book and many books, lots of books do it differently, but this book does A on the left endpoint. B is going to be your sort of artificial right endpoint that you then take the limit of. If the tail is to the left, we're integrating from negative infinity to b, so b is your fixed number here. That's fixed. That's a constant that's given. And then we're going to let a represent the artificial left endpoint. We will again find the area of this region here from a to b. We'll then take the limit of that as a goes to negative infinity. So here we're going to end up with a function of a when we do this definite integral right there. That's going to give us a function of a. And then we're just going to take the limit as a goes to negative infinity. And then the worst case scenario is if you have a 2-tailed function. And if you have a 2-tailed function, you have to do 2 improper integrals. You have to break it apart somewhere. Doesn't matter what you pick as your left endpoint for the right tail or your right endpoint for the left tail. It doesn't matter what value you pick. They just call it C here. Then you have to do this improper integral to the left. You have to do this improper integral to the right. Both of them have to give you a finite result in order to get a total that's finite. If either tail has infinite area, then the total area is infinite. So that's the worst case scenario because you have to do both, which is a pain, obviously. So it's twice the work. So let's try some of these unbounded, horizontally unbounded regions. We'll first look at a right tail. And so the strategy is to evaluate the definite integral from 1 to b. So the strategy is find this area from 1 to b, right there. But then we're just going to let b creep out to the right, i.e. take the limit as b goes to infinity and see if we get a finite answer. That's our goal. So with this first one, here's our function, 1 over x squared. And so what we are trying to figure out, the area is the integral from 1 to infinity of x to the negative 2 dx. With a horizontally unbounded region, it's really obvious that you have an improper integral because you see in one of the limits of integration an infinity, either a negative infinity down here or a positive infinity up there or both. So it's totally obvious when you look at, oh, it's improper, there's an infinity. So horizontally unbounded regions, it's really obvious that they're improper integrals. We'll see with vertically unbounded regions, so like a vertical tail instead of a horizontal tail, it's not as obvious because infinity is not going to be in the limit of integration. We'll get to that, of course. So we see it's improper, and the first thing you should write down when you see an improper integral is limit. That is how we evaluate an improper integral. So this is going to be the limit. As b goes to infinity, we're going to turn our improper integral into a definite integral. So there we now have a definite integral, and that integral is representing this area from 1 to b, and then we'll take the limit as b goes to infinity and see if we get a finite answer. Okay, so that's easy enough to integrate, so we just leave the limit out in front. We've already established that it's a limit as b goes to infinity. You don't have to keep writing that subscript on it. It's okay, just write lim. We already know it says b goes to infinity. So then we integrate. We get x to the negative 1 divided by negative 1 on the interval 1 to b. So regular integration technique, we just have a definite integral here, so we're just trying to make that a cleaner b. All right, so now we plug in our limits of integration. The limit symbol is still just waiting out in front. Let's simplify the inside there. Let's get rid of that negative exponent. So this is going to be minus 1 over x from 1 to b. We plug in our upper limit, plug in our lower limit, take the difference. Limit is still there, so it's minus 1 over b. Minus a minus is plus. And we're plugging in a 1, so it's going to be plus 1. So we end up with that. That is a 1. Oh, I guess I have to do it with that. So we're at the place where we evaluate the limit as b is going to infinity. And what is this limit as b goes to infinity? 1. So that tells us that this unbounded area, this area that has no bound, it just goes on forever and ever, that unbounded area is in fact finite. That area is 1 square unit. 1 square unit is the area beneath that curve. That's what we just figured out, that that's a finite area. And if we were to look at the rectangles here and their area, Zach mentioned a very important concept. You mentioned, I believe this is the thing that you mentioned, Zach, right? 1 plus 1 over 4 plus 1 over 9. And that represents the areas of these rectangles if we were to look at 1, 2, 3, 4, 5, 6, right? The widths would all be 1. The heights would be 1 over x squared, so 1 over 1 squared, 1 over that squared, etc. So this infinite series is connected to that. Right? So it will turn out that this infinite series, once we get to the next chapter where we talk about infinite series, which are very closely related to improper integrals, we will see that this is finite. We'll prove that in a slightly different way, but that series that you mentioned is connected to this graph. So these are going to zero fast enough for that infinite summation to be finite. Okay. Well, let's try. Any questions on that before we try another one?
So the one is the area.
The one is the area. One, a nice integer. 1 square unit, whatever units of measure.
Isn't this related to, like, I think it's Gabriel's horn, is this?
Yeah,
Yeah.
right there.
Yeah.
It's very similar to Gabriel's horn. So Gabriel's
8.9.
horn,
Oh, yeah, 8.9, yeah.
yeah,
it's one of our
Gabriel's
problems,
horn is
Yeah.
where we take 1 over x
Gotcha.
and we rotate it around the x-axis and we create this, what they call it Gabriel's horn. Gabriel's horn is unbounded, goes on forever in this direction. And what we will show is that the area, the surface area of Gabriel's horn is infinite, yet the volume is finite. And so there is a paradox with Gabriel's horn that says, okay, well, if the volume is finite, you can fill it with paint. If the volume is finite, you can get that volume of paint, pour it into the horn, and it will fill up the horn. But if the surface area is infinite, can you paint it? If the surface area is infinite, you shouldn't be able to paint it. But if you just filled the horn with paint, it's painted. Right? So that's Gabriel's paradox, which we'll talk about, and you can think about that. How can we have finite volume, infinite surface area, and justify that paradox?
Imagine the cooling potential.
Do you think that'll be on the test for you of the Gabriel's horn?
I know whether it will be on the test or not.
You want to share with the class?
Gabriel's horn will not exactly be on the test, but there will be an improper integral that has to do with volume, calculating whether it's finite volume or infinite volume. Okay, so let's try another horizontal tail.
My favorite.
So this one starts at 1 and goes to plus infinity, so we're imagining our starting point is right there, and then we're imagining all this area in here going on forever to the right. So it's unbounded, that curve never touches the x-axis. So that area here is unbounded, keeps on going forever. It looks like it touches the x-axis, but it doesn't. You know this. You zoom in and there's a gap. There's a gap between the curve and the x-axis. So that unbounded area, we want to know, is that unbounded area finite or infinite? Unbounded area, is it finite or infinite? So we look at this curve that generates, or the equation that generates, the function that generates this curve, 2 to the negative x. That's an exponential function. And so the idea, in order for an unbounded region to be finite, the curve has to approach the x-axis really fast. Do we think an exponentially decaying function approaches the x-axis fast?
Absolutely.
Yeah, absolutely. We think that approaches the x-axis faster than 1 over x squared. So our hunch is that that will be finite. Now when we look at this curve down here, to the left, we're looking at that graph and we're saying it doesn't look like it's approaching it fast. Right? It does not look like it's approaching it fast. So our intuition would be, it's probably an infinite area. The curve probably doesn't approach the x-axis fast enough. And a lot of times obviously the graphs aren't, foolproof, but when you look at the graph, usually you have a pretty good sense of whether it's going fast enough. So our hunch here is that, yeah, it's probably going fast enough. So what we do first is imagine a B. We just imagine a random B, and we're going to find that area. That area is a function of B. Depends on where you pick the B. And then we take the limit as B goes to infinity. So our area here,
Does 1 go to infinity?
1 is fixed as B goes to infinity. So 1 is the left endpoint of this region. And then the B tells us, okay, we're going to stop here and figure out that area as a function of B. And so once we have an area function, then we can take its limit and see if that's finite, if it has a finite limit. So the area, the integral from 1 to infinity, 2 to the negative x dx. Okay, so first word we write down in solving an improper integration is limit. And since we are going to the right, we're finding the area of a right tail, we let b go to infinity. It doesn't matter what letter you choose, b is just what this book chooses. So now we have a definite integral right there. And this definite integral is finding the area from 1 to b. So this is our area function. From 1 to b. So that's finding that area from 1 to b. And if you plug in b equals 2, you're finding the area between 1 and 2 on the x-axis. If you plug in b equals 10, area from 1 to 10, etc. All right, so now we integrate this exponential function. And when we integrate an exponential function, the first thing we get when we integrate an exponential is itself. Always start with itself. Then we have a little bit of stuff going on here. So itself. Reverse chain rule comes into play because the derivative of the exponent is -1, so we also have to divide by -1. We also have a modified base. The base is not e. And anytime we have a modified base for an exponential function, whether it's a derivative or an integral, we have to make a little tweak. And hopefully you recall, like if we had the function y equals 2 to the x, what is y equals 2 to the x's derivative? We first do the 2 to the x, and then we multiply by ln of 2. Exactly. We multiply by the natural log of the base.
So we divide by ln of 2.
So we divide by ln of 2. Exactly. It's just like reverse chain rule. When you're doing chain rule, you multiply by the derivative of the exponent, angle, whatever. When you do reverse chain rule, when you're integrating, you divide. Same thing with this. We have to divide by natural log of 2. So we're going to have an extra factor down here of ln of 2. And then this will go from 1 to b. Okay, so let's plug in our stuff. So limit is still just sitting out in front, waiting patiently. So we plug in the b. We're going to have a -1 out in front. We're going to have a 2 to the negative b. So we could write it this way, -2 to the negative b divided by natural log of 2. That's the first part, upper limit of integration. And then we subtract off what occurs at the lower limit of integration, but we're subtracting a negative, so this is actually going to become a positive. And when we plug in 1, we get 2 to the -1. And we still have our natural log of 2 in the denominator. So we have all of this. And this limit, once again, you don't have to rewrite b goes to infinity every single time. You've already written it once. I usually will write it again at the very end just to make sure. And looking at this first term, where does this first term go as b goes to infinity? 0. Because we have 2 to the negative b. Now, if that's not totally obvious, so this is a exponentially decreasing function. So an exponentially decreasing function goes like this to the x-axis. If it's easier for you to see these types of limits without negative exponents, which for many people it is easier, you could always change this and say, hey, let's get rid of the negative exponents before even thinking about this limit. So we would pull the 2 to the b down into the denominator and make the exponent positive, and then we still have this multiplication by ln of 2. And then over here, same thing, we could pop the 2 down into the denominator so that we have 2 natural log of 2, and then take the limit as b goes to infinity. If that's easier for you to see, that in the denominator we have an exponentially growing function. So this denominator is growing without bound, so this fraction is shrinking to 0. If it's easier to see it there, then go there. But either one, this part will go to 0. Which tells us the overall limit is 1 over 2 natural log of 2. So that is the area of that unbounded region. That unbounded region is finite in area, and that's what its area is. And certainly a lot less than 1. When we did 1 over x squared, we got a tail that had an area of 1. That's a lot less than 1. Because an exponential decay is going to approach the x-axis even faster, so it's going to have less area. All right, any part of that evaluation you want to look at? Ask about. Tim, did you just drive down from Longmont?
Boulders.
How was it?
A couple accidents, but not bad.
For me, it's really good because I drove here at like 7 in the morning.
Oh, that's one way to get around the traffic. Come at 7 a.m.
Yeah, there was a
When it
15-minute
wasn't
accident
snowing?
on 36 that was real bad.
Yeah, I was coming on 36 too. It was pretty messy.
I get off at 7 in the morning.
Yeah. My wife has to go to the hospital, and so I've got to drive on 36.
After it starts.
Okay, so let's try a left tail, which is why I have to just sit my phone periodically today, because she's got to go to the hospital.
Don't tell me what to know.
Okay, so for a left tail,
Zamboni sign.
really? I swear, man, they used to only do it on Fridays. I
At least
swear.
they're consistent with it.
Yeah, there's one consistent thing.
Yeah.
Bizarre.
They need to
Our
do
primary function is to teach at this place.
We need to do it at night
Exactly, at night or on a Friday.
Wait,
They do it
or on Saturday.
I want before so
Or
stupid you
Saturday.
like eat all.
Yeah.
well, in all
7 a.m.
fairness, with all the snow, it might be a trip hazard today.
Yeah.
They don't clean up.
Yeah, that could be.
Yeah.
Okay, so let's look at a left tail. So this, we are looking, our right endpoint is 0. So here is the right edge of the region. And then instead of a B, we're going to use an A. Again, it doesn't matter what you choose. And the first thing we're going to do is find the area of this. And the area of that is going to be a function. It's a function of A.
Can we just flip it?
You mean reflect it through the y-axis?
Yeah.
Absolutely. You could.
And then just treat it like,
You could, because it'll have a symmetric area.
okay.
Absolutely.
Alright.
You know, especially in a case like this. Now, if this right endpoint started at 2, you know, then that would flip over to -2, but you could flip it. Yeah, you could do a reflection through the y-axis. How do you reflect the function through the y-axis?
You flip the 0 and the infinity.
So you replace x with -x.
Yes.
So if you replace x with -x and then swap the limits.
Yeah.
You could absolutely do that. Okay, so let's find this area. We know that the area is the integral. We wanted to integrate from -infinity to 0. And we're going to rewrite this function. We know to integrate anything with a power in the denominator, it's easier to pop it up top. So that's going to be 2 minus x raised to what power if we put it in the numerator? -1/3. Because that thing is a third root in the denominator. Third root as a fractional exponent is a third, but then if we move it upstairs, it becomes -1/3. So there is the integral that represents this improper integral. It represents that area. And then the first thing we do is write down the word limit. Anytime we're solving an improper integral, and we are going to go from a to 0 as a goes to -infinity. So there's our improper integral. And the evaluation of an improper integral is to take the limit of a definite integral. So here is our definite integral. And this represents the area from A to 0. So that's what that represents. Because that's going to give us a function of A. When we integrate that and plug in the A and plug in the 0, we get a function of A. All right, so let's go ahead and do the integration. So we're just going to use the power rule. So we add 1 to the exponent. So we have 2 minus x. We add 1 to negative 1/3, and we get positive 2/3. Then we divide by 2/3, which means multiply by 3/2. And then we use the reverse chain rule because the base is not just x. So we have to divide by -1, which we'll just pop that into the exponent right, or into the numerator right there. So power rule, we add 1, divide by the new exponent. Reverse chain rule, we divide by the derivative of the base.
Wait, if we add 1 to the x, never mind.
Okay. Then we go A to 0. You answered your own question. I could see it in your eyes. So we've got that. And now we have that age-old constant thing. Should we just leave the constant? Should we factor it out? And again, like we've always seen in calculus, it does not matter. If it's easier for you to do the limit evaluation by factoring that constant all the way out to the front, totally fine. If your preference is just to leave it there, totally fine, does not matter. And so I'll factor it to the front. Make sure we plug in the upper limit first, and then we subtract off the lower limit. So pulled out the -3/2, so that part's gone. Plug in 0, 2 minus 0 is 2, so we have 2 raised to the 2/3 power. And then we're going to subtract off the antiderivative at A. We factored out the -3/2, so we just have this part left. So it's going to be 2 minus A. So we're subtracting the quantity, 2 minus A raised to the 2/3 power. And we have that limit to evaluate as A goes to -infinity. Okay. So A is going to -infinity. Let's start from the inside here. So when we look in here, 2 minus infinity, that's going to infinity, right? 2 minus infinity. And then what happens when we let that quantity go to the 2/3?
Still positive.
Still going to positive infinity. I'm not getting to that minus sign yet, right? I'm not at the minus sign, I'm just here. 2/3 power, remember that's like a root, that's the bird wing thing, it's going off to infinity. Slowly, but it's going to infinity. So that's still going to plus infinity there. And now, let's do the whole thing. 2 to the 2/3 is just a number. It's just a number. And if we subtract off infinity, 2 minus infinity, what's going to happen there? Negative infinity, but why are we, oh, negative infinity, but then we have that minus, okay? So all this is going to negative infinity. And then we multiply that negative infinity by a negative constant, and so this whole limit will end up being positive infinity. So that tells us that that area is in fact infinite. The area is infinite. So that tells us that the curve is not approaching the x-axis fast enough. Which we kind of gathered by looking at the graph. The graph gave us a clue. Most of the ones that are finite pinch down real fast. Okay, so evaluating that limit, everybody following the idea? If A is going to negative infinity, we have 2 minus infinity, so the inside here is going to positive infinity. If you raise a number that's going to positive infinity to this exponent is making that quantity approach infinity slowly, but it's still going to positive infinity. And then a positive number minus positive infinity is negative infinity, and then a negative times a negative is positive.
Got layers.
Layers. It's the onion. Getting to the inside of the onion.
Just count it.
All right, let's try the worst case scenario. The double tail.
Yay.
Double tail. So here's one with the double tail. And again, it doesn't matter what you pick as your midpoint or your break point where you're going to break it in half. 0 makes the most sense because we've seen that having 0 as a limit of integration is always beneficial. It's easiest. So let's go with it. Let's go ahead and break it apart right there. We're going to break it apart at 0. So we're going to have two improper integrals. Over here, we're going to pick an a, and that a is going to give us a function of a for this area. And then over here, we're going to pick a b, and that's going to give us a function of b over here on the right-hand side. So that in there is going to be a function of b. So function of a, function of b on this side, and a function of a on this side.
Will there be cases where we don't pick 0 for the middle?
I wouldn't always pick 0,
I mean,
but
if this is symmetric over -1, could you not do area from -1
Sure.
to negative?
you can do whatever you want.
Multiply it by 2 if it's symmetric.
But we have, if we prove that
it's
if we
symmetric.
prove that it's symmetric about -1, we could absolutely do what you just said. So if we can prove that this is symmetric around the line x equals -1, then we could just do 1/2 and double it. Yeah, absolutely.
But we don't necessarily know.
But we don't know that for sure. It certainly looks that way. Certainly looks that way. Okay, so here is going to be our first step. So we are going to have the limit. So let's do the left tail first. That's going to be as a goes to -infinity. And we're going to have the integral from a up to, let's see, 0. Yeah, we chose 0 for, I think, a good reason. And then we have this quadratic in the denominator that's not factorable, so we can't use PFD. So limit as b goes to infinity for the right part, that limit is going to be from 0 to b, and we have the same exact integrand. So same integrand. We've got that. Okay, so two limits, two improper integrals, and a quadratic, a trinomial that's not factorable. So what was our technique if we had a trinomial that wasn't factorable?
Complete the square.
Complete the square. If that trinomial is factorable into two factors, then we can use PFD. We can use partial fraction decomposition. But can't do that here. So let's go. So we're going to have a limit. And we could focus on just one of these because the integration stuff's going to be the same, right? So we're going to have dx divided by, let's see, what do we need as a constant for these first two terms to have a perfect square trinomial? 1. So we're going to write this as x squared plus 2x plus 1 plus 4, so that that part is now a perfect square trinomial. That will factor into x plus 1 squared. Perfect square trinomial. And then, let's see, let's write the second one. So the second one, we have limit 0 to b. And let's go ahead and factor it now that we see, because these are going to be identical. So we have that. Question?
And would you still not write the limit details if you have
subscript.
multiple limits?
I mean, it's obvious to me which one's negative, which one's positive. If you want to write them every single step, you certainly can, but I would never take points off of that.
Gotcha.
We want to be efficient. So what's our next step? We normally want a sum of squares with a 1. So we're going to do, not yet. We're going to, if we want to make that for a 1, we, favorite math F word? Factor. Oh, factor. So we're going to pull that out to the front of the integral. So this one will be a to 0. And when we factor that 4 out, there is no 4 in front of that x plus 1 business. So if you want to, you could write that, multiply by 1. And the idea is that you're factoring out that 4 in the denominator. And then we want that first term to be a square. So we'll make that x plus 1 over 2 quantity squared plus 1. So now we've got it all set up for integration. Both integrands are identical. And that integrates to arctangent. Sum of squares with a 1, arctangent. Sum of squares with a 1, we get arctan. And once again, we have a constant. If we want, we can factor it to the front. Don't have to, but factor it to the front. So then here we're going to have arctangent of whatever's in the parentheses, so x plus 1 divided by 2, arctan of that. Now we have to apply the reverse chain rule. If that was just x squared plus 1, we'd have arctangent of x. But it's not just x. It's a function of x. And what is the derivative of this function of x in here? Half. Right? This is 1/2 x plus 1/2. Right? That 2 distributes. That's 1/2 x plus 1/2. So the derivative of this inside quantity is 1/2. So we're going to divide by 1/2, which means multiply by 2. That makes sense? So arctangent of whatever's in the parentheses, but then the reverse chain rule piece says divide by the derivative of the inside.
I did a U sub, not the same answer, like.
Yeah, you can do a U sub. Yeah, if you want to spend more time on this problem, you can do that. And you can do U substitution.
Because you get the arctan identity, like arctan.
Yep, absolutely, absolutely. You can always avoid reverse chain rule by doing U substitution if you want. Absolutely, that will work. It just takes a little more time. And isn't the antiderivative of the other one the same? I forgot my limits of integration here. That's a to 0, and this is 0 to b. So same. Once again, we have constants on the inside. They can factor all the way to the front for each of the respective limits. So we can make this 1/2. So if I combine these two constants, this 2 pops to the front. The 2 is not inside the arctan, right? It can't go inside the arctan either. So it comes out to the front. And then we're going to have limit, and let's plug in our 2 limits of integration. We're going to have arctangent of, plugging in 0, we'll have arctan of 1/2 minus arctan of, let's see, we're plugging in a for the x. So it looks like an a plus 1 divided by 2. Arctangent of a plus 1 divided by 2. And then over here, same idea, we'll factor out the 2, giving us 1/2 times the limit. We'll first plug in the b, which will give us arctan of b plus 1 divided by 2. And then we subtract off the arctan of 1/2. Let me move that 0. How's that look? Is there any question on any of that? So plug in the upper limit, plug in the lower limit, take the difference. And now, let's look at our subscripts on the limit here. So this limit was as a goes to negative infinity. This one is as b goes to positive infinity. Okay, so let's look at this. And let's draw a picture of the arctan function just as a reminder. So arctan function is probably the only function you know that has two horizontal asymptotes. So arctangent is this graph. This horizontal asymptote's at pi over 2. This one's at negative pi over 2. So over here, as a goes to negative infinity, the inside is going to negative infinity. Negative infinity plus 1 is still negative infinity. Negative infinity divided by 2 is still negative infinity. So this part inside here is going to negative infinity. So what is arctan of negative infinity essentially? Negative pi over 2. So as x is going towards negative infinity, arctangent is going towards this asymptote, which is at negative pi over 2. So that whole quantity is going to be negative pi over 2. So we'll have 1/2. How about the limit of the first term? Limit of a
Goes to arctangent of 1/2.
1/2, right? A constant, the limit of a constant is itself. Right, this limit is as a goes to negative infinity. If there's no a, this doesn't have any bearing on the constant. Limit of a constant is itself. So that's going to be, an arctan of 1/2 is not a special angle. We don't know an angle in quadrant 1 that has a tangent of 1/2. We know a tangent of 1, tangent of 0, tangent of infinity, but we don't know a tangent of 1/2. So that just is what it is. And then this is minus pi halves. All right. And then the second one, 1/2. Here, the limit is as b goes to plus infinity. So this piece inside the arctan is going to positive infinity. And as we look at our graph, as x goes towards positive infinity, arctan of that goes towards pi over 2. So here we're going to have a pi over 2. Oops. And that pi over 2 is the constant part up here. And that constant is just itself. So we have that. And we have some cancellation, right?
Yep.
Here we have positive half arctan half. Here we have negative half arctan half. So these are going to cancel each other out. That and that are going to wipe each other out. And we're going to be left with positive pi over 4 plus pi over 4. Positive pi over 4 plus pi over 4. Pi over 2. So that is the area underneath that two-tailed graph. Twice as much work.
Well, we only have to integrate once, really,
True.
so it's not quite.
So we'll say that it's 80? It's about 80%. It's not quite twice as much. All right, any step there you want to ask about? Any part of the integration you are feeling sketchy on?
It's gonna be tough to remember inverse tangent for sure.
Inverse tangent's going to come up so much. You have to become one with inverse tangent.
Real quick, I skimmed over it. Could you go through about up there where you took the 4 out?
Yep. So
Or the
look,
1/4 out, sorry.
yeah, look. Let's look at this right here.
Oh, you have to divide by 4.
So when we are factoring out the 4, there initially is no 4 here to factor out.
You just took the square root
So
of
if we,
4.
yes.
Okay, I got it.
So we factor in the 4 out in front, and we want this written as a single square, so we want to include the 4 in that square, so we make it a 2, so that it's a single square. As soon as it's a single square, then it's in the arctangent form. Arctangent form is sum of squares with a 1.
That's nothing.
That's a sum of squares. That's not a sum of squares. Or it's not in the sum of squares form.
It's not arctangent.
What's that method called that you added the 4 before?
This right here,
Yeah, what is it?
arithmetic.
It's just multiplying by.
Just
So-
multiply by 1?
We're multiplying by 1, and we're using arithmetic to create a common factor of 4.
Yeah.
So we're multiplying by 1 in a particular way that we have this common 4 that can then come out to the front. And then this 4 is not factored out, so it's going to get swept into this quantity right here in the numerator. And that's why we want to write that as a single square. So we combine the 4 and the x plus 1 squared. Yeah, so we use, whenever we can, we want to, it's very much like that, that unit thing that they do in chemistry, what do they call that thing? Dimensional analysis, where you're just trying to deal with all the units. You multiply by 1 repeatedly, 12 inches in 1 foot, blah, blah, 60 seconds in 1 minute. So that's the idea, is if we can multiply by 1 to create that common factor that can then come to the front. It's like that dimensional analysis stuff. Okay, let's take our 10-minute break.
You notice I draw the lines.
Okay.
All right, let's try another one of these, or do you feel ready to try one yet, or not yet? Or?
Go for it. I'm so ready to fail at one of these.
You're so ready to fail at one. Okay, try this one. I think you could fail at this. Let's try it.
I love your confidence.
I actually
as
believe
long as
I actually believe you can do it.
As long as I fail forward.
Yeah,
we're
that's
good.
Fall
why-
forward.
That's why you're the teacher and I'm the student.
Yeah, you should be able to do this one. Now, just looking at your, let me make one comment before starting this one. When we go back to this double tail one, so we certainly can look at the graph, but let's think about the nature of the integral. So we've talked about the tail having to approach the x-axis fast. The denominator is quadratic, and we already did 1 over x squared, which was finite. And so that sort of is giving us a clue that, okay, well, 1 over x squared, if the nature of it is quadratic in the denominator, 1 over x squared is going to go to 0 fast enough. And when we looked at this one that didn't converge, it didn't have a finite area, what is the nature of the power on x in the denominator here?
Fractional.
So it's fractional power. It's an x to the 1/3, right? So that denominator is acting like an x to the 1/3, which goes to infinity a lot slower than x squared goes to infinity. And if the denominator goes to infinity faster, then the fraction is going to 0 faster. So what we're seeing is that if the denominator is at least going to infinity at a squaring pace, that's fast enough. But if the denominator is at a fractional pace towards infinity, a bird wing, not fast enough. So that's where we got divergence. Here we had an exponential, which we said goes to 0 faster. So just keeping that in mind, when we look here, the nature of this one is also quadratic. The numerator is like a constant, right? Arctangent of x, as x is going to infinity, it's approaching pi over 2. So the numerator, when you go far out to the right on the x-axis, it's just like pi over 2. It's like a constant. So the nature of this is constant divided by x squared being the dominant term in the denominator, so it's probably going to converge. So just as some ways to be you want to be sort of thinking, the math should confirm what we kind of think by generating some intuition here. So
So we put pi over 2.
yeah, exactly.
Yeah.
Arctan of x is pi over 2 in the long run.
Yeah.
In the long run.
Who needs math?
We got music.
I got it there. So that was just.
I know that.
That's
Actually-
not slippery anymore.
And then dx is equal to theta. Tangent squared plus 1. Tangent.
What technique of integration are we gonna use?
But if you just use U sub,
Well, imaginary.
Geometric substitution.
Imaginary
can't you
substitution.
just use U sub here?
U sub.
Yeah.
U sub.
Because
Is that what you
U
mean by
is
that?
tangent,
Yeah,
yes, tangent of
yeah,
x, du is 1 over x squared plus 1 dx. The derivative of tangent is the rest of the formula, the derivative of arctangent.
Right?
So I just did a lot of work for no reason.
Has everybody seen that U substitution works pretty nicely here?
That's like
If you let U be
it's like the reverse log
arctangent,
right there.
then the derivative of arctan is everything that's
It's an upside
left
down log.
in the integral. So it's really just a U to U.
Yep.
B U to U.
My degree, that was, I kinda see it now.
Dude,
Yeah, that was my integration technique, wait for the teacher to like,
stop that. That's not fair.
It works 100% of the time though.
Especially in math class,
Yeah.
because we have to go forward.
Yeah, who needs other math?
U is,
The biggest thing with improper integration is notation. You really got to get that notation down. You don't want to lose points for not putting the limit down. The biggest mistakes I see other than notation are evaluating the limits improperly. No pun intended.
I have it right along
tan of 1 is 4. No, because 1 over the bottom is the derivative of arctangent. The derivative of
When I
arctangent-
say that the definite integral is a function, is everybody totally okay with that by now?
So you're just multiplying.
That this is a function of, what is this a function of?
Yeah, you were right. 1 over du was
B,
was arctangent.
function of B, because that's the letter that's in the limit of integration. The x that's inside the integral is just a dummy variable, like you plug in for the x, so the x is going to go away. So the x is not really a variable, we call it a dummy variable because it's just there temporarily. Why are you laughing?
Because it's joyful day.
So everything okay about that? That whole function of B business, that is going to be finding the area from 1 to B. So that's what that function of B is finding. So if you plug in different B values, you'll get the area between 1 and that B value that you plug in. And I think we've heard that the U substitution is pretty straightforward. If we let U be arctangent of x, then its derivative is everything that's left. The derivative of arctan is 1 over x squared plus 1
dx.
times dx. So it's all that stuff.
We love
We expect it.
easy.
Come with the crazy.
Now, when we go ahead and convert to U, we have the choice. We could convert the limits to U limits if we want. Or we could put placeholders and go back to x, and it doesn't matter. What do you want to do?
Placeholders.
Placeholders? Because if we don't use placeholders, then we're going to be having limits like inverse tangent of b, inverse tangent of 1, which is not too hard, but still it's kind of a little bit messy. So if we use placeholder limits and just go back to x, it'll probably be easier in the end. And so the limit, make sure you keep the limit symbol out there. We're just integrating u squared over 2. U squared divided by 2 with placeholder limits. And we'll convert back. So we said that u was arctan, so we're going to get 1/2 arctan of x back to the u limits, excuse me, the x limits.
Who's this?
It is squared, yes. I just noticed that. So we will write this with the square on the far outside. We don't want to make that a -2 power. Right? This -1 is not a reciprocal. It's not 1 over tangent. Right? That has something very specific in its meaning. It's not a power to a power here.
See if we got it the right one, because U sub, now that I see it, is way easier than trade.
Both works.
So we could pull out the 1/2 all the way to the front, and then we have limit of arctan of b
I guess as long as all of your math is good.
minus arctangent
That's
of
the key.
1
Big assumption.
as b goes to infinity.
Both those squared, no?
And both of those are squared. I took off the square again. Why? Why?
I think you should write out ARC 10,
Yeah.
so you don't get confused.
Oh yeah, then it would be easier.
Yeah, arctan with a square is
So
easier than
that's pi
10 to the
squared
negative
over
1.
4 times tangent.
Okay, so then we can evaluate that limit. What is the first one going to be? As b goes to infinity, what is arctan of that quantity?
Pi over 2.
Pi over 2, and then we square it. We're going to get pi squared over 4. So pi squared divided by 4 minus arctan of 1 is
Pi over 4.
pi over 4. Arctan of 1 is the angle on the right side of the unit circle with a tangent value of 1, which is pi over 4. And then we square it, and we get pi squared over 16. So we have all that. And then we're going to have 1/2 multiplied by common denominator of 16. So we have 4 pi squared minus 1 pi squared, which is 3 pi squared, divided by 16. And so we'll end up with 3 over 32 times pi squared. So this improper integral converges. So we say converges if the limit is a number. We say diverges if it goes to infinity. We can also say that the area is finite, and that area is unbounded. That goes on forever and ever. That unbounded area is finite, which is a little unsettling in some ways.
It's like if you had that shape, you could paint it with 30 seconds pi squared gallons of paint, but you couldn't make a line, a wire that was long enough for the edge, which is a really weird thought.
Start thinking about sizes of molecules.
Did you get UDU instead of U over DU?
So when we take, do you follow the derivative step here?
Yeah.
So this dx is in the numerator, right?
Yep.
That's in the numerator. So this part right here, oh, I have to picture with that, I guess. So this part right here is what gets replaced with the du. So that du is on top. Right.
Yeah, if you think of it as,
So if we think of that as dx over 1.
and if you think of it like arctan of x times 1 over x squared plus 1 dx, that whole bit is du.
Okay.
It's in the numerator.
Yeah, that piece is in the numerator. And the differential always has to be in the top, right? When we think of our integral symbol and the differential, there's sort of one symbol, essentially. It's got to be in the top. We never can divide, unless you're doing some weird related rates thing where you have du dx times dx dt or something where you're canceling differentials. For us, basic integration, we always have an integral with one differential. And that differential has to be in the numerator. All right, so let's talk about Gabriel's horn again for a moment. So Gabriel's horn, we are taking the function 1 over x. So the function 1 over x in the xy plane right here, that function 1 over x goes on forever this way. We are going to look from 1 to infinity. When that rotates around the x-axis, it creates this Gabriel's horn. And what we are going to find in a moment here is that we will have finite volume but infinite surface area. So let's do the math on that part first. So the volume part is the part I want to focus on first. Surface area we'll get to in a minute. Surface area is a little sneaky. The volume, though, we are going to use the disk method. So if we think about drawing a vertical element right there, that's going to create a disk, and that disk has area pi r squared. R is the function. So here's pi times the function squared. So pi r squared, this will find the area of the disk at x, and then if we integrate the area, we will get volume. So volume is the integral of area. And right off the bat, we see that, oh gosh, we're dealing with a square in the denominator, so we expect convergence. We've already seen this one, essentially. So here, we're going to have the limit. When we integrate, we add 1 to the exponent and divide by the new exponent, which puts a minus in front. And then we're going to go from 1 to b. So we're going to have limit. And if you want, you can factor out the minus pi. I didn't factor it out here. It doesn't really matter. So it's going to be minus pi over b. Minus a minus is plus. Pi divided by 1. And this limit is as b goes to infinity.
So that's pi.
Pi. So the pi over b part, this is going to 0, correct? As b goes to infinity, a constant divided by a number going to infinity is going to make the fractions go to 0. So that is our volume. Pi cubic units of paint, if we were painting it. All right, any step there on the volume that you are not sure about? So disk method, pi r squared is the area of a disk. The radius of the disk is given by this blue function here. The function is 1 over x. So we square 1 over x, we get 1 over x squared. Integrate, we end up with pi. So finite volume. Surface area, a little more complicated. So surface area, surface area, again, 1 to infinity. And for surface area, we do what we always do. 2 pi r times ds. So here is the 2 pi r. Again, the radius is the 1 over x. It's the function. So 2 pi r is circumference. And then we multiply by ds. This part right here is ds. And ds, we've learned, is found by taking the square root of 1 plus the derivative squared times dx. So that's ds. So if we look at our ds, this is going to be 1 plus, we square that, we get 1 over x to the 4th times dx. So that is our ds. Right there. Okay, now with this surface area, there's going to be some subtleties here. So let's jump to the next step here. So here's where we're at, right here. So we haven't really done much math there. All we did was get rid of those parentheses, I guess. Okay, so we have that. Do you agree that this square root piece, if we take it away, that this inequality would be true? So if we look at these two things, this piece right here is bigger than 1. Do you agree that that's bigger than 1? X is on the interval 1 to infinity, so 1 over x to the 4th is always positive. 1 over x to the 4th might be microscopic, but it's still positive. If you get out to x equals 10 million, 1 over 10 million to the 4th is microscopic, but it's still positive. This quantity right here is greater than 1 no matter what. Correct? Greater than 1. So if that part's greater than 1, if we take it away, then we're going to have something that's less. All right? So if you have a bunch of stuff multiplied together and you take away a piece that's bigger than 1, you've shrunk what's left. Right? What's left is smaller. Okay, so that is a subtle piece, because this integral here we cannot do with mortal means. If we try to do that with substitution, it's a nightmare. We can't do it at this stage of the game. But we can definitely establish that it's bigger than this. If we take away a piece, a factor that's bigger than 1, we've shrunk it. Right? All right. Is that clear to everybody? If you take away a factor bigger than 1, you're shrinking what's left. If you have the number 6 and you write it as 2 times 3 and you take away one of those factors, what's left is smaller. If you take away a factor bigger than 1, you've shrunk what's left.
So all you're saying is if you still come out with infinity,
Yes,
it's just a smaller infinity.
exactly. If we find that this integral here is infinite, if this improper integral is not finite, if it's infinite, something bigger than it must also be infinite. That's exactly going to be our logic. And our hunch right here, when we look at that denominator, the nature of this denominator is that we only have we have x to the 1. Right? That's not growing very fast. X is going to infinity very slowly. We saw x squared goes to infinity fast enough to get a finite result. But this, let's check it out. Okay, so that's bigger than 1. So notice this right here. Let's see, how do we do this integral? So if we are going to integrate from 1 to b, as b goes to infinity, 1 over x dx, what is the integral of 1 over x?
Natural log of x.
Natural log of absolute value of x. We don't need the absolute value because x is always positive in this context. So 1 to b. So we get limit natural log of b minus natural log of 1. Natural log of 1?
0.
0. So that equals 0. Natural log of b, and we're taking the limit as b goes to infinity. That limit is infinity. Natural log is growing, albeit slow. It's still growing to infinity. So this limit is infinite. So if that limit is infinite, then this has to be infinite, which means the surface area has to be infinite. So therefore, surface area is infinite. And so then you can start to think about that paradox that they write in a lot of these calc books. If the horn has finite volume, you can fill it with paint. If it has infinite surface area, you can't paint it. But if you filled it with paint, you just painted it because the surface is microscopically thin. What's the resolution?
An atom.
An atom. That is the resolution. Because in our mind, we say you can't paint an infinite surface with a finite amount of paint. Why do we have that restriction? Well, because if we take our gallon of paint, you can paint one big disc. But if you shrink the molecule in half, you could paint a bigger disc. If you shrink it in half again, you could paint a bigger disc. So in the end, you actually could paint, mathematically, you could paint an infinite surface. It wouldn't be very bright, and it's mathematically, because you can't cut a molecule of paint in half. But
we do it with
that's
vapor
it.
metal disposition. We lay an atom thick.
Whatever he just said. Are we talking about
We literally lay a layer of nickel, like a couple
One.
atoms thick.
what's our magic substance that's so amazing now?
Graphene.
Graphene. That stuff is incredible. Yeah, I remember with there used to be a TV show called what the heck was it called?
Atomic vapor.
There's a TV show about science, the incredible acts of science, or some funky name, but it's really good. There's all sorts of graphene stuff on there. You can make it in your garage. It's like, whoa.
The other lesson is don't try to apply real life circumstances to infinite shapes. Because
There is that.
Don't work out.
Yeah, when you get to
Don't work the way you want
infinity. Robert?
Yeah, the square root, how you took that away,
Mm-hmm.
so you just know it's 1.
We know that this quantity here is bigger than 1,
Just took it away.
and we just took it away. It's sort of like if
Yeah,
we,
Infinity plus one, which is infinity at the end.
so if this quantity here is bigger than that. It's kind of like if I have 2 times 7, right? That's equal to 14. If I take away one of the factors, I'm going to have a quantity that is now less than what I started with. But if I take away a factor that's bigger than 1, I'm left with something that's smaller. That's what we're saying. So if we take away a factor that's bigger than 1, we're left with something that's smaller. And that quantity that's smaller we can show is infinite. So anything bigger than infinite must also be infinite.
Okay.
So that's kind of our logic stream that we're using to.
Could you sort of also split it into 2 integrals and then say, this integral must be a positive value and this integral?
How could we split this into 2?
Like at the first step, can't you take that and make it 2 integrals, pi, or 2 pi times 1 over x to the 1 to infinity times,
No,
or,
you
no, you
can't.
can't split because they're multiplied. That's only if
Yes.
it's pluses.
So an integral of a sum you can split into 2 integrals. The integral of a plus b is the integral of a plus the integral of b. But the integral of a times b,
That's
you
why-
can't break it apart.
That's why calculus is a class.
Which we were talking about in the lab last week. You can't make that integral of a times integral of b.
Right.
You can only distribute an integral like you can a derivative. Right? It distributes, so yeah.
And that's why this is a class, because you can't just do that.
Okay, let's take a look at this crazy looking function. And we see the graph and we're like, there's no way that this area is finite because that's approaching the x-axis very slowly, right? So the region bounded by f and the x-axis on the interval, and this is going to be rotated around the x-axis. So the question is, okay, when we rotate that around the x-axis, is that going to create a finite volume? Kind of like Gabriel's horn, where we got the finite volume. Well, let's find out. So we've got this function here. We're going to rotate it around the x-axis, and when we pick an arbitrary x, the disk that's created will have a radius of r. So that disk is going around. The radius is the function. So the area of that disk is equal to, so the area of the disk, k, right, is pi r squared. And we just said that the radius is given by the function. So we want to square that whole thing. X squared plus 1, all that squared. So we have that. So there is the area of our disk. Let's maybe simplify this before we go on. The numerator becomes x. The denominator becomes x squared plus 1 to the 2/3. That's a third root, so that 3 is in the denominator of the exponent, third root, and that square is in the numerator. Okay, so that's the area. Volume is integral of area. And so we're going to take the limit, and they tell us here we're starting at 0. So we're going to take the limit from 0 to b as b goes to infinity. That'll be our setup. And we integrate area to get volume. So we're integrating that function. So my first question to you is, what is the nature of this integral, or this integrand? So if we wanted to speculate whether this is going to converge or diverge, so far in our mind we know that if we have an x squared in the denominator, that's going to converge. Or if it grows even faster than x squared, if we had an x cubed or an x to the 4th, or something exponential. So what is the nature of that denominator?
X over x to the 4/3?
So we have x, so if we just strip away the constant, so we have the x in the numerator, and in the denominator, if we strip away the 1, that's x squared to the 2/3, which is x to the 4/3. Okay, Now, if we want to push this x into the denominator, that becomes an x to the negative 1, correct? And our focus is usually on the denominator. We're looking in the denominator. Does the denominator go to infinity fast enough for convergence? And so then this becomes 1 over x to the 1/3. So once again, we have a fractional power on x in the denominator. And we've seen that that is not a function that grows fast enough to cause the fractions to go to 0. So we are expecting divergence. We're expecting non-finite area. Volume, non-finite volume. Since we're finding volume in this case. So let's see. Pull out the pi. Limit. Okay. Technique of integration here. U sub. U sub works great. You might say, oh, we could use trig sub. And you could, because we see a sum of squares. But we only go to trig sub if something easier is not available to us. The first thing that we should be noticing is that if you take u to be this quantity inside the root, its derivative is present, right? Its derivative is in the numerator if we do something like that. X dx is there. So if we can use u sub, we'd rather do that than trig sub. Trig sub's always a lot more work. So we'll go with just u sub. And let's see, so our limits of integration are going to change. So we have x dx, which is du divided by 2. So there's du divided by 2. I'm going to put the division by 2 out in front. And then u raised to the 2/3 power is in the denominator. These limits, they're not too bad. Let's convert these ones since we didn't convert the last ones. When x is 0, u is 1. When x is b, u is b squared plus 1. Okay, so now we're in that old scenario where we have a power down in the denominator. We move it up to the numerator so that we can use power rule. So we're going to have pi over 2 limit. And this is going to be the integral of u to the negative 2/3 du. Okay, so power rule. Add 1 to the exponent and we get u to the 1/3. Divide by 1/3 means multiply by 3. And then we have our limits of integration are these. The 3 can come all the way out in front, and we could make that 3 pi halves. All right, and then we have limit. Now, this limit, remember, is as b goes to infinity. So let's get that back on there. And let's see, what's left? We plug that in right there. We get b squared plus 1 to the 1/3 minus 1 to the 1/3. 1 to the 1/3 is just 1. So we're taking the limit of that. And what is that limit? Infinity. So b squared plus 1, as b goes to infinity, b squared plus 1 certainly goes to infinity. And then 1/3 power, that's the bird wing, that's going to infinity, and infinity minus 1 is still infinite. Infinite times a constant is still infinite, so we end up with plus infinity as our volume. So we have infinite volume. That make sense? Or is there any piece of it that doesn't make sense? Any piece you want to ask about? But you can see how important it is to be able to perform the integration part without thinking too hard, because there's so much other stuff going on. You want to make sure you practice your integration so that you can not get stuck on that part.
How'd you get the b squared plus 1 for the upper limit?
So for the limits of integration, these limits of integration are the x limits. This is the relationship between x and u. So if we plug in x equals 0 there, we get u equals 1. If we plug in x equals b there, we get b squared plus 1.
Okay.
You see it?
Yeah, I was writing when you
Yeah.
put that up there.
No problem. Yeah, ask. I can't tell if it makes sense or not. All right, should we go to vertically unbounded? So vertically unbounded is the advanced case.
No, I'm so scared of vertical unbounded. You're gonna get all the tests.
So just make sure that,
These numbers are real.
okay, you got to the hospital.
All you do
Yeah.
is just arbitrarily decide that y is x.
Okay. Yeah, a little sketchy. It's like, wasn't supposed to smell like this. We weren't supposed to have a squall.
You gotta do the
Right.
Troy fun fact where you just write not equal to
I mean,
on the
theoretically,
task
wouldn't it
and
work
it's
if
true.
you just flipped your Cartesian plane by 90 degrees? It's the same
Yeah.
thing, you're just translating it.
Yeah, if you
Translations.
can translate your equations into, if you flip your stuff, or if you integrate with respect to y instead of x.
Okay, so here is what's tricky about the vertically unbounded. With the horizontally unbounded, you see infinity in the limits of integration and you know, oh, something's different. I don't have two constants, I've got an infinity there. You know it's improper. When it's vertically unbounded, you don't see it in the limits, right? This is just from C to D. We don't see an infinity in either of those places. And one of the things that's brushed over a lot in Calc 1 is that you kind of you just sort of mindlessly look at that and integrate, plug in the C, plug in the D. But there was a subtlety in Calc 1 with the fundamental theorem that said this turns into the antiderivative evaluated at these endpoints only if this function is continuous on that entire interval. This function is not continuous on that entire interval. There's an asymptote at A. So this function is undefined at that value A right there. And I highlighted, I wanted to be highlighting over here. This function here has to be continuous on AB. And that function is not continuous on AB, right? There's an asymptote at A. And so what we do is something very similar to what we did with the horizontally unbounded. We pick a point that is closer to the B in this case, and we are going to calculate this area right there as a function of C, and then we're going to let C creep over to A. We'll get this here we're going to get a function. So this area in here is going to be a function of C. And then we're going to let C approach A and see if that limit is finite or infinite. So same idea, but it's just not as obvious because your limit of integration is not infinity or a negative infinity. So same idea down here. If the asymptote is on the right, we are going to find this area right here. For these vertical ones, he always uses a C. So this, again, is going to be a function of C inside here. And then we're going to let C approach B from the left. Up here, we're letting C approach A from the right. So we're doing one-sided limits here. If we've got, that situation, same idea as before. We have to break it apart into two integrals, do two improper integrals, add them together. If one of them is infinite, the whole thing is infinite. So vertically unbounded regions. Let's try one. Okay, so when I look at this graph right here, I see two tails. I see a horizontal tail down here and a vertical tail up there. That horizontal tail certainly looks, if you look at the graph, it's sort of it's reasonable to say, oh gosh, that's going to be finite down there because it's going to the x-axis really quickly. But this vertical axis right here, the y-axis, this does not look like it's grabbing the y-axis really quickly. So it appears that that's finite and that's infinite. That's what it appears. So, well, let's take a look. So this is our function that we've already looked at. And somebody remember, what did we get this area? Was that 1? Is that the one that was 1? We did, there was the very first example we did. We went from 1 to infinity for x squared. So let's check the vertical tail. So the vertical tail, again, not obvious that it's an improper integral. But as soon as you think for a second, you're like, oh, wait a minute, I can't plug a 0 in there. This function is undefined at 0, so there's an asymptote at 0, which means it's an improper integral, which means the very first word that you write is limit. Anytime we're dealing with an improper integral, we need to use a limit. And so he uses a c for these vertical ones, and we're going to approach 0 from what side? Right. From the right. So if we imagine our c value, let's just plop it in right here. There's c. Then we're finding this area where we're over to 1. Let me redraw that. 1 is right here. There's 1. So c is going to be in here somewhere. So we are finding this area as a function of c. And then we're going to let c creep over to 0, but it's coming in from the right side. It's a one-sided limit. So we're going to let c approach 0 from the right. All right. And then we're going to rewrite this. So this will be an x to the negative 2 dx. And we're going to go from c to 1. So c to 1 is this region in here. We're going to find a function of c that represents that area. And then we're going to take its limit as we go to 0 from the right. Let's go. So limit is hanging out in front. We do our regular business here, x to the minus 1 divided by negative 1. So there's our antiderivative from c to 1. Plug in the 1, plug in the c. Limit just hangs around. So we're going to get negative 1. Right? 1 to the negative 1 is 1, and the negative's in front. Minus a minus is plus. Reciprocal of c we write as 1 over c. And this is as c goes to 0 from the right. Very tempting to say that this limit here, 1 over c, is 0. But it's not, because we are taking it at 0, not at infinity. So what does 1 over c approach? Yeah, this is going to approach infinity as c goes to 0. And everything's positive, right? We're approaching 0 from the right. So we're coming into 0 through positive values. So that denominator is always positive, but it's getting super close to 0. And as that denominator gets closer to 0, those fractions are going to increase. 1 divided by 0.1. 1 divided by 0.01, 1 divided by 0.001, right? Those numbers are creating bigger and bigger values, so that's going to go to infinity, which means that this whole thing, infinity minus 1 is still infinity, so this goes to infinity, so we have infinite area.
Can we really just do that? Like if you give us a problem and just say, oh, that looks like it goes to infinity in the y, just solve that and say, oh, this goes to infinity, so the whole thing. Or just skip the other. Like up there, you've got 1 to infinity and 0 to 1.
Yep.
If the horizontal tail, we know. Yes.
So I think what you're saying is if one is infinite, is the other finite, and vice versa?
Well, I mean, they are.
Not always.
I'm not saying they always are.
There's
saying,
one exception.
Yeah, but what I'm saying is if we see that, we can just skip it, right?
I don't know about
It's like
skipping.
area under the whole thing kind of thing. Like if we see one of them is infinite. If you want
Yeah.
area from
So the question,
zero
this
to
is more of a comparison. Like you're not going to see on an exam both of them.
one.
You're gonna see one of them.
But if you had, for instance, from 0 to infinity, and you
One to
proved
infinity?
it- well, no, from 0 to infinity, and you proved it from 1 to 0.
Oh, is that what you're asking?
Yeah.
Oh, if you go
part
from,
of it's infinity.
got you, I understand, I
Yeah,
understand.
it's kind of like you did with the real.
Yes, yes. I thought you were comparing these two integrals, but you're saying if it went from 0 to infinity, yeah, if one of the tails is infinite then. But what is going to happen, that the pattern that I thought you were pointing out is that if it's getting closer to x, it's going to be peeling away from y. If it's getting closer to y, it's going to peel away from x. It's going to be like a whack-a-mole thing.
Oh.
If you grind closer and closer to y fast, then you're pulling away from x and you're approaching the x-axis slower.
You give me too much credit.
What's the exception?
The one exception is 1 over x. 1 over x diverges in both.
Because it's symmetric over.
1 over x is symmetric and it's going to have both infinite. Both tails are going to be infinite. That's the one
If it's
exception.
Around the slant asymptote, this,
Say that again.
if it's symmetric around the slant asymptote all the way through.
If it's symmetric over.
Yeah, there's no other power of x that's going to be symmetric around the y equals x line.
Because like you said, it's either gonna pull away from.
Pull away from y and
Or pull away from x.
yeah, one or the other. It's going to be totally whack-a-mole thing.
And as we showed with the surface area of Gabriel's horn, 1 over x goes to infinity.
Yes, exactly. So let's notice the powers of x. So what we are seeing then is if the power of x in the denominator, if it's bigger than 1, horizontal is finite, vertical is infinite. And the opposite is true if the power is less than 1. So if the power is less than 1, the horizontal tail is infinite, and we're going to see that the vertical tail is finite. We're going to see it's one or the other. And the threshold is 1. If the power is bigger than 1, we have convergence here, divergence there. If the power on x is less than 1, we have divergence there and convergence there. That is what that's what we're going to see right now. So here's the opposite case, where we've got a fractional power of x in the denominator. So the horizontal tail, just looking at the graph, you can kind of see that that's going to be infinite and that's going to be finite. So we just have to remember that threshold, and we have to remember that we're looking in the denominator. So if the power of x in the denominator is fractional, we're going to have vertical converge, horizontal diverge. So let's go ahead. Let's do the horizontal tail over here first, because that'll be quick. So this is going to be the limit as b goes to infinity, integral 1 to b. We're going to write this as x to the negative 1/4 dx. Power of x in the bottom, pull it up to the top so we can use the power rule. Limit is hanging around. We get x to the 3/4 times 4/3. Add 1 to the exponent, you get 3 over 4. Divide by 3 over 4 means multiply by 4 over 3. So we end up with 4 over 3 out in front. So we can just focus on the limit. We're going to b to the 3/4 minus 1 to the 3/4. 1 to the 3/4 is 1. So b to the 3/4. What's the limit of that as b goes to infinity? Infinity. So anytime that exponent is less than 1, we've got a bird wing. And that's going to go to infinity. Infinity minus 1 is infinity. Infinity times 4/3 is infinity. So horizontal tail, diverge. So we went from 1 to infinity. We get diverge there. And we will see that we get converge on the other piece. So let's show it. So we're going to do the same type of thing. Also notice that it's not obvious just by looking at the integral that it's an improper integral. You have to start to be proactive and think, oh, it looks like a definite integral and it feels like you could just do the definite integral process. But you have to remember that this is not a definite integral. This is an improper integral because the function is undefined at 0. Okay, so we're going to take the limit as c goes to 0 from the right, and we're going to go from c to 1. So same antiderivative. We're we're gonna get 4/3 x to the 3/4. Same antiderivative. Plug in our limits of integration, and we could factor out the 4/3. Might as well just get it out of the way so we can think about the limit without the constant in there. So factor out the 4/3, we've got limit. We're gonna have 1 to the 3/4, which is just 1, minus c to the 3/4. And the limit is as c goes to 0 from the right. So what is the limit of c to the 3/4 as c goes to 0? 0. 1 minus 0 is 1. 1 times 4/3 is 4/3. So you just have to be vigilant about making sure that you're going to the right value. So limit as b goes to infinity, limit as c goes to 0. Because you end up with the same nature here, right? C to the 3/4, b to the 3/4, but if b is going to infinity, that's totally different than if c is going to 0. So we get converge or finite area over here. So converge on this side. And that's going to be our pattern that we're going to see again and again. Fractional exponent, converge vertically, diverge horizontally. All right. Okay, we'll do this one. Yeah, we'll do this. We'll do this one. Some of these are hard. Okay, so -3 to 1. So here's our interval that we're integrating over. -3 to 1. Again, kind of looks like a definite integral. And it's not until you look more carefully that you realize that it's not a definite integral. It's an improper integral because division by 0 makes it undefined, gives you an asymptote. So, as soon as we know that it's an improper integral, we know that we have to use limit. And c is going to approach, let's see, the asymptote is over here at -3. So we're approaching -3 from which side?
The right.
From the right-hand side. So we're going to approach -3 from the right-hand side. So we're going to have the integral from c over to 1. Okay. Power in the denominator, it's easier to move it to the numerator because then we can use the power rule. So we've got that. Any issues up to that point?
Or it's not an issue, but what if you had an asymptote on both sides?
So if you had two asymptotes, you would do the same thing. That's kind of like the case if we were integrating from -4 to 2. You'd have to break it apart into two pieces. So if there was another asymptote over here and this was like a big U, you'd have to break it apart in the middle and do two separate integrals.
Like if you had tangent, if you wanted to.
Yes, exactly. So you can only have one bad point, one bad spot per indefinite integral, improper integral.
So you have to split it into multiple.
Split it into two parts.
So then if you had AC current, you have to approximate.
Say that again?
If you were like AC current
Mm-hmm.
and you have that almost square wave that you get,
Yep.
you would have to do an improper fraction on maybe two of them and then assume it.
That's where you're going to end up using Laplace transforms, and you can do it all at once.
Oh, okay, all right.
Yeah.
Yeah, sounds good.
Laplace transform is going to make a square wave really easy to deal with, or a step function.
Yeah.
Otherwise, you would have to do what you said. Okay, so power rule. We have our base, 2x plus 6. We add 1 to the exponent and get a third. We divide by the new exponent, which means multiply by 3. But we also have to divide by 2 for the reverse chain rule, or multiply by half, either way. Right? So power rule, we add 1 to the exponent, divide by the new exponent. And then we have to divide by the derivative of the base. So divide by 2 or multiply by half. Those mean the same thing. And then we go from C to 1. Okay, constant, let's factor that to the front just to get it out of the way. So we have 3/2. Limit. Plug in the 1 and we get 9 to the 1/3 minus quantity 2c plus 6 to the 1/3. So limit of all of that as c is going to go to -3 from the right. So let's look at that part over here. This doesn't have a c in it. The limit of a constant is itself. If there's no c that the quantity depends on, then the limit of that is itself. There's no c.
8 to the 1/3.
Say that again? Oh, maybe. Oh, did I
C does
add
not
2
go-
plus 6 incorrectly? 2 plus 6, that's the hard part. 2 plus 6 is the hard part.
I hate when that
Then that just makes it 2.
Yeah, I was thinking, oh, it's funny that they didn't give us a perfect cube. I didn't think, oh, I added wrong. Okay, so what about the 2c plus 6?
Goes to 0.
This goes to 0, everybody agree? Because we're plugging in -3. -3 times 2 is -6, so that all adds to 0. So then our final answer is 3. Great, 3.
3 halves times 2.
Okay? And this is what we expected. We expected a finite vertical tail because we have a fractional exponent on the x. X is raised to the 2/3. So fractional exponent, we're going to have a finite vertical tail, but if we did a horizontal tail here, we would find that that would be infinite.
Gotcha.
Wait, is it possible to have a finite on both tails?
Mm-mm. I mean, maybe there's some funky function that you could create. If we're dealing with standard common functions, powers of x in the denominator, no. Maybe there's some wiggly weird function you could create. But
I mean, if you
I've never
shifted
seen
the
one.
X and the Y,
if you what?
if you shifted in both the X and the Y,
But as soon as you shift, then the asymptote's shifting with you.
that's true, but if you're only
So-
going to the axis, you only
It
calculate
won't go to infinity in both
Yeah,
directions. It'll go to a finite point in each direction.
Yeah.
Like,
Oh, if you take away one of the asymptotes so that you chop it off?
Yeah.
Yeah, Then we don't have tails though. Like in the case where we have both a vertical tail and a horizontal tail, I've never seen a function that has both finite.
I wonder if it's possible.
You could create the Zachary function.
Like you look it up.
And then realize some
Right.
mathematician years ago figured it out.
Yeah, someone probably already figured it out. No doubt. No doubt.
Wait, they figure it out right now, or
No, I'm not going to figure it out right now.
that's
But I'm going to look
interesting.
it up just to make sure.
Get it
I don't think it's possible.
You don't do it in.
I think it's a good question though. You'll do it in Calc 6. Okay, here's another one.
I think I went to Calc 6.
No, that's what
That's right. Yeah, it's named something different.
Calc 6 is named something different. Okay, so here we've got a right endpoint that's at natural log of 3. Left endpoint that's at 0. So we're going to create a C value right there. We're going to find that area. And that area is going to be a function of C. That area in there will be a function of C. And then we're going to take that limit as C goes to 0 from the right.
So
Okay.
you're integrating with respect to y. Did we just flip it over the xy and
No.
say it's an x graph, or
I mean,
like?
so this graph right here, that's a good
Is
question.
for it's if you had e to the x, I think, right?
Let's that's a good question because I probably just graphed it as e to the x and didn't even think about that.
So it's It's the correct graph, just flipped over the x equals y line.
Because let's ask ourselves, where is this undefined? This is undefined at 0, right?
Yeah.
So it's undefined at 0. So 0 is definitely the asymptote,
Okay.
right? So
It's defined at y equals 0.
it's
but the way
defined
it's
at
graphed-
y equals 0.
The way it's graphed, we're just doing it with x.
It's just
instead of-
reflected.
yeah.
Yeah, that's a good point. This, yeah, I definitely did everything as if it was x's. I did not graph x equals e to the
Yeah.
y, yeah.
Okay.
Good, good point.
Y as a variable.
Yes,
Yeah, we're just using y as a variable here, not as a.
exactly. It's just a dummy variable. The graph is to give us an intuition for the improper piece of it, but, yeah. So, but if we graphed it as x equals, yeah, you're right, it would look differently. We'd have a horizontal asymptote. Yeah, good observation. So, let's rewrite it then. So we know that we are going to have limit. We know that we're going to use a C because it's a vertically unbounded region here. And we're going to go to 0 from the right. So 0 from the right. And we are going to have an integral that goes from C to natural log of 3. E to the y over e to the y minus 1 to the 2/3 dy. All right, what technique of integration do you think we're going to use?
U sub.
U sub. Beautiful.
You love U sub.
What are we going to let u equal?
E to the y minus 1.
And this is only going to work if the derivative of this is present. And sure enough, the derivative is in the numerator. Right? The derivative of e to the y minus 1 is e to the y. So that's going to allow us to write limit. So we're going to have, isn't this just going to end up being u to the minus 2/3? Right, the e to the y dy is the du. In the denominator, we have u to the 2/3, so we're going to bump it up and change the sign. Limits of integration, if we want to switch. Kind of a pain. Let's just go with placeholders for this one.
Yeah.
Let's just do that. So then we're going to get limit u to the 1/3 divided by 1/3 with placeholders. Then we'll jump back to our original variable. We can pull the 3 out to the front. Get rid of the u, so that's going to be e to the y less 1, all raised to the 1/3 power. And now we have our original limits. Back to that. All right, everybody see where we've gone so far with that u sub? So now we're going to plug in our limits of integration. So we're going to have 3 multiplied by limit. Plug in the ln3 first.
3 minus 2.
So we get 2 to the 1/3. Everybody agree with that? Then we get the whole messy piece. We're going to have e to the c minus 1 all to the 1/3 power. So all of that. And this is as c goes to 0 from the right. And this piece on the right, where does that go as c goes to 0?
1 minus 1.
So that's all 0. And the 2 to the 1/3 is a constant. Limit of a constant is itself. Nothing happens there, just sticks around. So we end up with a final answer of 3 multiplied by the 3rd root of 2, which you could write in several ways. That is our final answer. 3 times the 3rd root of 2.
Why isn't the ln3 just 3? Oh, it is? No.
That's just how ln's and e's.
Okay, so it's minus 1, so it's 2.
Yes. Okay, I'm with you now. So when we plug in this here, e to the ln of 3 is 3, and then 3 minus 1 is 2.
Okay. I see
Is
what
it?
it is.
Yeah.
Dash L.
Right, so this part here, when we substitute it in for the y, reduces to 2, and then we have 2 to the power of 1/3. That makes sense?
Yeah.
Other questions on it?
Will we be having the graphs for the?
If you have something totally funky, I will give you graphs. You know, and I'll tell you if something's an improper integral or not, you know, just so you're not wasting time thinking it's not an improper integral.
Now we just have to read.
Now you have to do what?
I forgot to read last time.
Oh,
said
of course you
use-
did.
Use substitution.
Super important.
Yeah.
Read. Read.
Yeah, just skipping the reading part on the test really hurts sometimes. You're like, wow.
That's one important thing. When you're doing your homework, it's very easy to get into the, okay, I got it wrong. Now I'm just focused on getting the right answer and not reading the question again. It's really important to sort of associate the words of the question with the technique that you're using. You know, so if you read the question once and then you start and you got the technique and oh, I'm doing this technique again and again and again. But it's easy to disassociate that technique from the words if you're not refreshing your mind every time you're redoing the problem. You know, just because you want to be able to get on a test and recognize the strategy right away. And the way you build that skill is to make sure that you're, every time you do a problem, you're connecting the words that the question is asking with the technique. You know. All right, let's stop.
Oh, yeah.
Week 6, right? Are we week 6 now? Or did we just finish week 6?
Week 7.
I think we're week 7. Yeah, we are. We just finished week 6 yesterday. Say again?
We're 3 classes.
Oh, lucky you.
No, are we?
Oh, I don't know. I'm not taking the test.
Thursday.
2 classes.
Wait, when? What's the date right now? 27th. Oh, it's a week from Thursday.
Yeah.
Oh, this class is flying.
Spring break.
We don't have the worksheet.
Oh, yeah, spring break's on.
Oh, it is not. I will. Oh, thank you. I will distribute that. Sorry about that. I totally. So the next worksheet, I'll distribute it right now. I thought I'd already done it. I forgot I didn't.
Oh, yeah, that's kind of important.
That's important.
It's
Now.
going to do Thursday. Yeah,
It's due this upcoming Thursday.
due in 2 days.
No, it's not even 2 days, is it?
Yeah, 29th.
If there's not enough time, we can.
Wait, am I pretty good?
What's
Or
that?
am I just not bad?
I forgot about the worksheet.
Oh, yeah, sure.
I'm going to have a call.
Yeah, I was actually having a stress week today that I forgot the worksheet. And I woke up and it was